Welcome back. I am Pavlos, Protopapas, and I'm going to lecture today. All right. Hope everybody's doing well. Saturday. Tomorrow, remember, what day is tomorrow? 3?
It's Sunday.
It's a special day, at least in US.
Is it?
Very special. It's Father's Day. So remember your dad.
Yes. Yes, Professor.
As a father, I'm speaking here. Right. So don't forget to say Happy Father's Day to your dads. All right. We have enough students to start. Today's lecture 4 is the last lecture of the AI 4A, which is the reinforcement learning, but we prepare another lesson for you, for anyone who is interested. We're going to release it on Monday. We're just doing some minor tweaks. We're not going to provide that lecture. It's for more advanced things, but since we prepare it, we decide to release it due to the fact that only 4 lectures we have, and it wouldn't be enough time to go through that. But it's pretty good stuff, so you should pay attention to it. You should look at it. All right, so today is lecture 4. What we're going to do today is we're going to introduce deep neural networks into reinforcement learning. Okay, let me start sharing. Are there any administrative questions? Any questions you want to ask now before I start? Homework is released. Didn't see much action on the forum, which usually means you haven't started yet. All right. So lecture 4, deep Q learning. A little kind of review what we have done last time. We talk about tabular Q learning. So in the Q learning, what we did, we find the optimum policy even for actions when actions are selected according to a more exploratory or even random policy. So remember, we're doing this exploration. So the idea is to learn the Q values associated to every state action pair, and we create these tables, right? And from the tables, we did an exercise, and then you did a lab that hopefully help you to understand and digest these things. So the pseudocode we have, we initialize our table for every S, except always the terminal. So we're gonna loop through each episode. And now remember the difference between Q learning and SARSA, as opposed to we did before. Here we're gonna be starting with one state, and we don't know the transition probability. So we're gonna be kind of probing the system, right? So for each step of the episode, we take action by some policy, and then we take the action and we observe. I mean, we select the action given some policy, they take the action, and then we observe the return and the new state. So the reason we have to observe is because we don't know the transition probability. So we just make the action and see what happens, right? Then we update our Q value to be the previous Q value plus some change, some delta, and we in front of it, we put some learning rate, some small factor. And we maximize over all the possible other actions we can do from that point forward. And then that's going to be the new state, and we keep looping, okay? So that was kind of a review. Now, what was the problem? Issues, the tabular Q learning will work only in cases where the number of actions and state space is relatively small, because we create a table. You could imagine to make a big table, but then there's a limit to how much you can do. So we talk about the frozen lake. The frozen lake is nice and easy. There's only 4 actions and 14 states that can make a nice, easy table. And then we talk about backgammon, that is too many states, too many combinations and everything we can do, right? So, and this is repetition. You can imagine if you have a big computer and a large memory to do that. However, if you start talking about the helicopter where the state space continues, then we're stuck, right? And so we do not want to have an entry in the Q table for every millimeter that the helicopter moves, right? So we need a new method. All right, so that's where we left last time. And what we're gonna do today is first we're gonna do Q learning, deep Q learning. And that's we're gonna introduce deep neural networks. And then we're gonna double it, double Q learning and double deep Q networks, okay? All right, this is a fun topic. I really enjoy this one. Now I start again with my little cartoonish thing. So imagine now we have the panda on his hoverboard, and he has to go through all these things. And now there's, instead of 4 rows and 4 columns, I have 100,000 rows and 100,000 columns. The panda is complaining. He said, "You expect me to remember and recall all this? You got to be kidding me." Okay. So what should we do? Well, one way of doing it, and I think I already introduced it last time, is we find a way to approximate this cube. So we approximate and in order to interpolate or extrapolate, right? So if I have a function that gives me the correct number for any S and A, that's what I want to do. Instead of having a table, now I'm gonna have a function that will give me the Q values, right? So, and if you remember from AI2 and AI3 and AIX, what we learn is that neural networks are pretty good function approximators. So let's use a neural network for that, right? So now we estimate the Q star, which is the optimal policy, to be approximate to Q, but now there's a parameter theta, which is the theta here will be the parameters of the neural network, the weight and the bias. Okay. And then once we know the best Q, remember the optimal policy is the one that maximizes the Q value for that particular action. This is a thing that we keep repeating. Remember, Q value is the Q star, the optimal Q, is given an action, any action you want. Going forward, it will be the optimal path, right? But for the Q value, the first action is taken deterministically, has nothing to do. So the optimal policy is you optimize the first step. Remember that, right? The Q is always conditional on one action. So the Q star for a state and a given action is after I take the action the best possible. So the policy here will be just maximizing over this action, the first action. Okay. Looking at your faces, you're still digesting this. I know the Q value and the state value confuses you, but that's the point, right? The Q has one action already taken. All right, now let's talk about deep Q learning in kind of general terms. So it became popular by a company called DeepMind, which by now you all know what DeepMind is, right? DeepMind is a company based in UK, in Cambridge, funded and started by George Hassabis, who is actually from Cyprus too, like myself. And then it became very popular because they start beating the AlphaGo and all these things. But one thing they introduce a lot in their algorithms is reinforcement learning. So it kind of was used to solve a lot of games for Atari up to superhuman level by combining reinforcement learning and deep neural networks at scale. Okay, I don't know if they were the first ones to do it, but they were the company that actually popularized reinforcement learning a lot, and a lot of their algorithms based on that. So what we're going to talk about is Q-learning and deep neural networks techniques, and in particular, something called experience replay, which I'm going to explain in a second, right? So deep Q-learning replaces the standard Q table by a deep neural network, which maps environment states and actions to Q values. Okay, so I have the state and I have the action. I want the Q value. All right, so it's as simple as this. I have an input, two inputs, the state and an action, and I'm looking to find the Q value. So I'm just going to start a neural network, right? There's no problem with that. I think it seems quite straightforward to that, right? So when I have a neural network like that, the first thing I like to know always is what's the input, what's the output. Okay, the input is the state and the action, and the output is the Q, right? We have to think what is the loss function, which we're going to describe, and of course, what is the deep neural network. The deep neural network here doesn't matter. It's going to be fully connected. That's usually what we're going to be using, and the loss function will be important. Now, a couple of little details here. When we look for the policy, right, or if we change the policy and we want to update all these things, we need to change the neural network, right? But to find the optimal policy, we have to investigate all possible actions. Okay, so that means that there's two things that you can see. That one means that I have to try all possible actions to find out what's the best one, right? Or what else can we do? We don't have to try all possible actions. Let's see if we can guess that. Or what I'm trying to do is maximizing. Let's look at this here, right? We're trying to maximize the Q on the neural network over all actions. So one way of doing it is to try all different actions and find out the maximum, right? Or how do we maximize something?
Gradient ascent.
Yes, so we need to do gradient ascent. And to do gradient ascent, we need the
Loss function.
on top of the loss function. What do we do to the loss function to do gradient ascent or gradient descent?
Back propagation.
And the back propagation involves
minimization of
Chain rules.
Chain rule.
and the chain rule is a product of
derivative.
thank you.
Slope.
I was getting there, right? All right. So that means back propagation. That means we have to back propagate through this network to come here, right? And that could be very expensive, right? So that's a problem, right? So we need to figure out how to maximize over A in order to avoid this problem.